Typically, when a person first starts encountering the idea of continuity, it's defined informally as a function whose graph can be drawn without ever picking up your pencil. So this might be graphically an example of something that is continuous over that interval, and a different graph that would not be continuous would be something like this. And that definition works just fine as an informal definition to address the idea, but we can be more rigorous with our definition of continuity. So there are three things that must be true if a function is continuous. Right? The first thing is that the limit as x approaches c of our function exists. So at whatever point you're asking about, is this function continuous here, does the limit actually exist? The second thing is that f of c must exist. That means that the function must be defined at the point when x has the value of c. And the third thing that must be true is that the limit as x approaches c of f of x must actually equal f of c. Right? And if all three of these conditions are met, then a function is said to be continuous. Let's look at a number of examples and talk about whether the function is continuous or not, and if it's not, really why it's not. So our first example, graphically, we've got a picture where the function has a limit approaching 3 from the left, a different limit approaching 3 from the right, so the limit does not exist. So this breaks property 1. A second graph might look something like this. We have, in essence, a linear graph, but there's a hole at x equals 1. So although the limit exists, because you're approaching both the same value from the left and the right hand side, f of c, in this case f of 1, does not exist. So that's why this is not continuous. The same would be true for a graph that looks something like this. The limit exists, say at -2, but the function's actual value isn't there. And we could say that it's defined to be this. So the limit could be 2, but the function's value could be 3. So this breaks option number 3. In example D, we have a graph that's not smooth at all. It means that it's coming to a point and then headed up. So what's happening here? This is continuous because the limit exists, the function's value exists, and the limit and the function's value are the same. So this is an example of something that is continuous. So hopefully you're getting a sense of these things about why something is or is not continuous based on our more rigorous definition. Now there's a couple things to note about whether something is or isn't continuous about specific kinds of functions. Right, polynomials would be continuous as long as all three conditions are met. Right, so all polynomials that meet all three conditions are continuous. If you have a rational function like y equals f of x over g of x, well, this would have to be discontinuous if g of x equals 0. Right, that would be the locations where it would not be continuous. And there's two cases involving radicals. One would be odd roots, so third root, fifth root, seventh root, so on and so forth. These are continuous everywhere. right, and consider what the graph of something like this looks like. And the other option are even roots. So an even root of something f of x. These would be discontinuous whenever f of x is less than 0. So just some things to be aware of. And in the next portion of the video, next section we'll look at just a number of different example problems involving the idea of continuity.